Okay. Live stream. Okay, I think we're showing we're live. Awesome stuff. Okay, evening guys, whatever time it is in your country. For the first live stream that I want to do, I thought it would be a good idea to do it in this way first. And by that, what I mean is we're going to not do a live amplifier repair in the workshop, partly because I haven't got the equipment yet to do it, but I want to see how the live stream works. I want to check my internet connection is good enough so that you guys can actually see the live stream and the audio, and it's kind of, you know, okay-ish quality through my current hardware and the current internet connection. I've been doing some tests, but a real world test is always the better option. So because some limitations with open broadcast software, I'm actually doing a kind of janky method of streaming this video to you. What I've done is I've got a video which I made of a amplifier repair, and what we're going to do is we're going to watch it together live, and you guys can ask live questions, and I can do live Q&A whilst we're watching the video. I can pause and rewind, etc. So yeah, I thought that would be quite a nice mix. So it's not a live repair, so you don't get the length of a live repair video. It's still an edited video, so we edit out all the long bits, but you still have the aspect of live about it, where you can ask questions at the time that it's actually happening. So let's give this a go. And the camera which I'm using for myself here is some Logitech webcam from like 2001, hence why I probably look like a potato of pixels just now. Yeah, my hardware is very out of date. Let's give this a go then. So I'm going to hit play on VLC, and hopefully this works nice and smooth. Alright, so today we're going to be looking at a pair of amplifiers which you may not recognise by the brand, but you will recognise, I'm sure, a lot of you, by the board layout. Now this is a brand over here in the UK which is a very entry-level budget brand called Bassface. Interesting name. I wouldn't have chosen that one myself, but there we go. It's just the name of a company that buy amplifiers from China, put their brand on it, and sell it over here in the UK and throughout Europe. I've got two here on the bench. I haven't even looked inside them yet. Hopefully they'll have different issues, so I can show you hopefully power supply and output section repairs for these style of boards. Now the boards that these use have been around for absolutely years, and you will have seen them. I'm trying to think what brands we both share over the pond. SPL Dynamics 1500D. What else? Maxima. The Loudest.com used a version of this board, and many more brands. Let me know how that looks, okay? How that looks to you guys. It looks like it's playing smooth, got no drop frames on my end, so let me know. Now when I say the SPL Dynamics 1500D shared this board, okay, it's not the exact same board because they do slightly different power, but it is the exact same circuit. All that they have done is the factory will have different variations of this circuit for different power levels, and they get gradually bigger, but the actual boards, they look virtually identical, just slightly different sizes, with maybe different components or different numbers of output FETs and power supply FETs, etc., and bigger transformers and inductors. The design of this circuit is, I wouldn't even like to guess, like flipping 15 years old, perhaps, maybe longer. It's very basic, very cheap board design, but it works if you know what you're doing. It's not a very forgiving board design. Some brands will have worked with a protection circuit to make it a little bit more reliable, more stable, more open to abuse. Oh, these are the V4s. Okay, nice. Whereas other brands may not have done that and gone for cost-saving options. Now, so you can see this board here. It's a very common layout. We've got power supply with two transformers, and these transformers will be driven by power supply FETs here. So we'll have, what have we got? 1, 2, 3, 4, 5, 6, 7, 8. So we'll have this transformer here driven by these four and these four on this side, like this, and then this transformer driven by these four and these four like this. So that's the power supply section. All the drive circuitry for the power supply section is here, surface mount components, and then the output section starts pretty much here. We have the rail capacitors, and then over this side we have the output MOSFETs, which are usually 640Ns, really old, and they could use much better nowadays, but they're pretty reliable, commonly used. The drive circuit for the output section is here on this little board here. The third era says, about clamping these amplifiers in dB drag in Europe. Well, we'll get to see what they clamp and what the wave looks like at their rated, well, at their clamped power. It's a little bit less than rated, you'll see, and the V3 and the V4 are quite different in their power that they actually put out. Along with the input OP amps, etc., and some protection circuit. It's a very basic protection circuit, which is all over here. The output section does have some protection triggers, but no protection circuit of its own. It just sends a trigger to this circuit to tell the power supply to turn off. So yeah, let's see what we got going on with this one then. There is now these boards. Bassface have done different revisions of this board. V1, V2, V3 and V4. The V1 was shite. It was literally the cheapest options from China. The board was orange, very thin, crap solder jobs, traces were thin, etc. None of these were CA'd down with silicon, nothing. And they were going pop bang whiz all over the place. V2s were a bit better, but they still used the cheap orange board. The problem with the orange board is when something burns on the board, it actually carbonizes, and you end up with a board which is conductive, which is no good, because then all of a sudden all of these pins are then conducting through the board, and you've got to cut the board away, which basically renders the amplifier irreparable. But I did do a repair on one that had some very heavy carbonized damage that was conductive on the board. Had to cut away the board. I'll put up a picture here, and you can see there how much of the board I had to cut away that was conductive to then put the effects back to where they should be on the traces, and we did get the amp working, and it was all good, and it's still working to this day, so that's a result. But yeah, the V3 then introduced the blue board, much thicker, doesn't carbonize when it gets hot, thicker traces, better build quality all round. It only had 4 output rail capacitors, and it didn't have quite a thick cable here, and these weren't quite as good, these transformers. And then the V4 just went even thicker on the PCB, 8 rail caps on the output, and yeah, a better build quality all round. It's like a kind of finalized, perfected version of the original amplifier. Okay, so Mike Roberts says, does the power supply section output in parallel to the output section? They work independently. The power supply provides power to the output section. So you take 12 volts, the power supply section takes 12 volts and boosts it up to plus and minus rail voltage, so plus and minus 50 volts or plus and minus 80 volts. So the amplifier then uses that power that the power supply section has generated. So they need to work together, but they do work separate, and the power supply section doesn't have anything to do with the audio output as such. So because the protection circuits on these are kind of naff, if the amplifier goes down, it usually goes down in quite a bad way, and there's usually lots of burnt bits on the board and things. So this one actually looks pretty neat. There's not a lot going on here in the sense of visual signs of damage. Let's take my other close-up camera and let's have an inspection. As for the transformers in the power supply section, in the transformers, they are driven by 2 separate banks of power supply FETs. So you'll notice you have FETs on one side of the board and FETs on the other side of the board. And this amplifier, these Bassface ones, on opposite sides of the board, you have FETs that drive one phase of the wave, so it will drive it maybe up, for example, and then the other ones are the outer phase side of the wave. So you have the FETs on either side, and it drives one transformer like this, push pull push pull. The transformers They are kind of in parallel, but they go through separate rectifiers. So on the other side of the transformers, you have rectifiers, which change the AC from the transformer into DC rails for the output section, and those rectifiers are kind of paralleled by the fact that they all share the output rail capacitors. But the transformers themselves aren't in parallel, but they are sort of paralleled by the time they get to the rail capacitors. So yeah, nothing horrific. This is the power supply section. Usually if the output fails, it will pull the power supply down with it, leading to a direct short circuit across the power terminals, which cooks these FETs on the board. Nothing really looking bad there. Output section doesn't usually show physical signs of damage, and there isn't any here to see either. Okay, so what's going on with this one then? Time to take out the multimeter and let's have a look on diode beep setting. First things first, always when you open an amper, if there's no obvious visual signs of damage, go through multimeter on beep setting so you can get a oral aid of what's going on. And firstly, what you want to do is put the positive probe on the amplifier's positive and the negative probe on the amplifier's negative. And what you should see on the multimeter screen is it will beep probably for a second and then it will start climbing, like so. And that means that you are charging the power supply capacitors, which are these guys. So that means that there's no short circuit across the power supply section. The MOSFETs, if there was a short circuited MOSFET, then what would happen is it shorts between these two and this would just beep continuously. But okay, power supply, we're pretty much safe to say that the power supply is not broken, because if the power supply does break, that's what happens. We could obviously have the issue with the drive circuit, but it's very rare for the drive circuit just to randomly develop a fault with nothing else happening. So let's move on to the output section then. What have we got going on here? We've got the 640Ns. So again, same thing. We want to probe this time the leg 1 and leg 3, which is the gate and the drain. And we have should see a value on here depending which way we put the probes. This one is climbing because we're charging capacitors. If we put it the other way around, we should see around about a number between 300 and 500. Okay, 530, that's fine. So yeah, just want to go ahead and check the rest of them, and if they are all showing a number 530, if they're all saying about the same number, and that's fine. If it beeps continuously, then we've got a dead output MOSFET. Huh. Well, this one doesn't seem to have any issues. Drastic issues anyway. Doesn't seem to have any drastic issues. Okay, there's no dead MOSFETs in this amplifier. So now we've discovered that there's no dead power supply MOSFETs, no dead output MOSFETs. Let's apply some power to this board now on a very low current supply, which we can do safely, knowing that there's no dead short MOSFETs, and see why the customer is saying that this doesn't work. Right, let's add some power, see what happens. I've got the amplifier remote on a foot pedal, which, I thought it was just a silly hack, but it's so handy. It's brilliant. Right, first of all, let's put the probe onto one of the drains of the power supply FETs, and we should see on the scope a nice wave building for the power supply. Yep, there we go. I had the scope on the wrong setting. Yeah, that built up pretty quick and nice, and we've got a good looking square wave on the power supply. The amplifier itself has actually come on and we have a blue light, and I know from experience with these amps that clicking sound at the start as the amplifier was turning on was the power supply slowly charging the rail caps, which means that the rectifiers are working well, and it means that we have good we have the rail voltages correctly in the output section, and we have a blue light. So let's turn the scope up to higher numbers so we can see the output switch, and we should have the switching wave on the output section. We've got the rail voltage there, and we have the output switching wave. Woohoo! So what the bloody hell is wrong with this amplifier then? I'm going to leave this running for a minute or so just to make sure it's not like heating up. I'm just going to plug RCAs in just to make sure it's actually outputting an audio wave, and then we'll bench test it, make sure it's doing rated power. But if they can't see anything else wrong with it, then obviously I'll just go back to the customer and say, guys, working fine, man. I've done a check. I'll do a full check over, make sure that. Actually, let's just give these transformers a quick wiggle. Put this back on the power supply.
make sure that there's no short leads on the transformers.
Yeah, so the power supply which I'm using when I do tests like this and when I'm seeing whether a repair has worked or not is 9 volts. It's about 9.5 volts, and 90% of car amps that I work on do switch on with 9.5 volts, and the lower input voltage transpires to a lower output voltage on the output rail, which makes it safer to work on. It takes less time for the capacitors to discharge when I want to do some soldering on the board, and it also makes any heating issues, if there's still a problem with the amplifier, it doesn't blow as quickly as it would do if it's on 12 volts. So I have a bit more time to discover the fault and rectify it before any damage occurs.
Seems alright. These are pretty well seated down. Output sections, make sure there's no short on the inductor.
And yes, that is right. Jody Howell, the amplifier takes DC, turns it into AC, and then turns it into a top and bottom rail of DC that the output section then turns back into AC for the speaker. It's an absolute nightmare. If only the car provided the correct rails to start with, you'd only need half of the size of the amplifier for a certain power. This is stupid.
Nope, seems alright. So yeah, bench test time for this one then, and yeah, we'll contact the customer and say seems to be alright.
So when you're probing the board like that, so you saw here I'm probing. That's where we are. We're at 1036 on the video. So if we go back and have a quick look at some points where I'm probing. So this probe point is the power supply. This is the power supply wave. So I'm probing pin number 2 on the power supply MOSFETs, and that will probably be a 65N60 or a 3205 or a Z44N MOSFET on the power supply. And the power supply side is most of the time nearest to the power inputs. So you probe pin 2 of the power supply MOSFETs, and you can see the wave which is being sent to the transformer ready for it to be boosted up. If you probe pin number 1, you can see it looks like the same sort of wave, but it's the drive wave coming from the drive circuit which drives this FET, and it will be a much lower voltage, maybe like around 5 volts. So the drive wave on pin 1 is 5 volts, and then the actual wave that drives the transformer on the output of the FET on pin 2 is about 14 volts RMS of AC. And then we were at about 1036 on here, so let's skip that over a little bit. I forgot to change the flipping I'm getting used to this OBS software. Sorry. So yes, that's the power supply switch wave. The output switch wave looks like this, and to probe that, it depends whether you're probing high side or low side. So the output section will have a high side and low side. That's how it works. The low side, if you want to check this wave on the low side, then you probe pin 2 of the output MOSFET. If you want to check the high side, you probe either pins 1 or 3, which will have a very similar wave to this.
Bench test, and yeah, we'll contact the customer and say seems to be alright. Alright, so this is amp number 2, and this is actually a V3, not a V4. So yeah, 2 different versions of amplifier here he sent me. You can see that because we have got 4 instead of 8 rail caps, and the board is a slightly lighter blue colour. It's a bit thinner, it just generally feels a bit cheaper. This is a really thin, flimsy case ground wire. This wire is much cheaper. Yeah, it's just not as beefily put together, but still much better than the V1 and V2. So this amplifier then, on the power supply, we got on the power supply, no issue on the power supply, no shorted FETs on the power supply. Output section then, let's have a look, see what's going on over here. So first ones, we're just going to check between the 2 end legs, and we have a good number. So is this amp going to be working as well? And we have another issue in his car elsewhere. Okay, whew, we actually have an issue then. So out of the 2 amplifiers, we have this amplifier has a dead output section on one side. So yeah, we have this side has shorted FETs. So we have 20. So if we go through each one, we've got 1, 2, 3, we've got 6 output FETs here. If we go through each one, so the first one between the 2 outer legs measures a 21 ohm resistor. Next one is a 21, next one is a 21, next one's a 21. Okay, no, the next one is dead short. So from that we can make a good guess that these 3 FETs didn't die. We just lost a single one here so far. And let's go ahead and check the next one.
Yeah, there's much less
That
in the
one
V3
might be
than there is in
okay.
the V4.
That one also might be okay. So we may have only lost one singular FET then in this amplifier, being this one. We won't know for sure until we pull them all out and whack them on the transistor tester. But if that is the case, what some people might think to do is like be okay, cool, no worries, let's replace that one FET. No, unless you happen to have the exact same batch from factory that are the rest of them, you can't do that. You have to replace all 6, and that's because they are all running parallel to drive the outputs. So we have to replace these. We need 6 new 640Ns, which I believe I have. Got quite a few in there. And I've got even more brand new ones in here, so that's good. Cool, let's start tearing this down then and seeing what the fault was. Right, board is out, so let's remove this one dead FET then and see whether it was that only one that died. Causes for this: the back of the board does have some of this white crap on it. Now this is scared the crap out of me then. This usually is caused by condensation, so if the car is cold inside, moisture in the air, and the amp gets warm, then the water droplets will form on the board and then leave a residue here, which can sometimes be conductive. And if it is between the driver board pins here, as you can see, sometimes voltages leak and it can lead to this happening. So we're going to clean this up with the alcohol, and you can see there around the edges like little waves almost of the condensation there that's evaporated. So perhaps that's the issue. We'll clean it up and see what happens, but first things first, get this danky ass FET out, and then we'll see if there's any more damage elsewhere. So let's use my nice big tip to heat up all 3 legs at once. Use the old workshop hoodie. I do wear this hoodie in a lot of videos, and I'm not janky. It's my work top, it's my work hoodie. Obviously clean as fuck clothes on underneath, you know, man staying fresh up in here, but obviously got to wear the janky top so that the thermal paste doesn't get on my nice clothes. So yeah, so that was easy enough. FET is out, and now we're just going to check to see whether that short, that 22 ohms, has disappeared on the rest of them. Yeah, it has. So no more 22 ohm resistor on any of the rest of these FETs. So that was the only one that died. Now, interestingly enough, I did say that we would have to replace all 6 of these. But because I've worked on so many of these, I usually salvage any ones that are working from a batch that didn't blow. So I might, lo and behold, have one of the same batch, which is really weird. You think, what the hell, how is that possible? But this batch of MOSFETs would have been bought in their tens of thousands, maybe even hundreds of thousands at the factory, and they would have been used in a huge number of this amplifier as it was produced. So chances are that I've got one that's the same batch that I pulled from a previous one of these that I worked on. So you can see here the original batch that we need is V6SU, and this is the manufacturing code for this batch of FETs when they were made. And as you can see, I've got a nice big pile of old salvaged FETs from old amplifiers, and you can see how many amplifiers use the 640Ns. And lo and behold, in that pile I have a singular V6SU. So this is a brother of these FETs, and they were made in the same batch in the factory run, and so they all work perfectly together, which means that I don't need to replace these other ones which didn't die. There is a chance, however, that these ones in here, 1 or 2 of them, or maybe all of them, have been damaged by the issue where this one blew. They just don't show a short circuit, and the way in which we can tell that is obviously by fitting this one in here, powering the amplifier up on a small power supply, and checking to see whether they actually switch and whether they get warm. Heat is the key to whether these FETs are working properly. If any of them are slightly out of tolerance, they are leaking, or they're not working, or are no longer a MOSFET, then the amplifier will either not come on at all, the waves will look horrific, or there will be heat generated very, very quickly on the output section. If we have good switching, we have operation, no issues, audio, and stone cold operation out of the heatsink, then there is 99.999% that these don't have any issues, and we can go ahead and run a bench test and run a 45-minute endurance test just to make sure. So let's whack this in and then see what happens.
Yeah, definitely. Mitchell Roberts saying that the one FET can die just due to manufacturing tolerances, where this one was maybe had or was just a poor quality when this FET was produced. Yeah, definitely that can happen. It's strange. The Bassface DB 1.3 and similar boards tend to kill single FETs a lot more often than I ever see before. So the 640Ns are used in a huge range of amplifiers. They're very flexible FETs, and they're used across the board in amplifiers ranging from sort of 500 watts RMS all the way up to around 3000 watts RMS. Other board designs that use these 640Ns I don't tend to see as many that kill a single 640. This could be one of two things. It could be that the protection circuit in the Bassface amplifier or this style board is much quicker. That means that only one FET dies and the rest of them get saved. Hence one dies. In the other boards where either none die or loads of them die all at once, it could be a couple of things. It could be that actually those boards are slightly better and they don't tend to kill a single FET if it's the board that's doing it, or if it is the fact that the 640N, just one of them was a poor build from the factory and it dies, then these other boards don't have as fast a protection circuit, so rather than just one dying, they all die, which makes it look like there was a more sophisticated issue with the amplifier rather than it just being a single FET. But yeah, these single FET issues I've seen lots and lots of times on these Bassface amplifiers.
Just quickly clean up the jank on this board, which may have caused it to go down in the first place. This is kind of annoying. I really would love a ultrasonic cleaner. That would be fantastic, but they're quite expensive and wouldn't be cost effective yet for what I do in my work. So we're going to have to stick with the old alcohol, and obviously this is kind of annoying because these rags, they snag on all of the electronic legs and you get this crap. So I really need some rag that's not going to pull and leave bits of fluff all on the back of the board that I then got to pick off, because that's a little bit annoying, but it'll do for the time being. It's a bit like when your cat gets on your duvet or whatever, or your sofa, and starts doing that thing with its claws. That's pretty much what's happening here, just in reverse. Let's apply some power then. Let's see what we've got going on. On the scope, we've got the top line is the 9 volts of worth of input, and this will turn into a square wave which will fly around all over the place, and this middle line here will become the output switch wave, so hopefully, if this amplifier works. So let's just flick the remote on the foot pedal. You can see we've got the red light come on, which means that the amplifier is receiving power and it's about to switch on. So let's hold it on. Okay. Cool, well that means that the power supply is working and the output rail is building. Cool, boom! So operation then, and on the scope you saw the power supply wave going a little bit crazy, so I'm going to remove that scope probe because we know that the power supply is alright. So let's just check for heat, because that few seconds of, wow, that's freezing.
Just quickly on the scope there, you saw there was 2 waves. One was the output switch wave and one was the power supply wave. The reason that one of them looked like a big mess and the other one was nice and stationary is because my scope can only focus on one wave frequency at a time. So the power supply and output switch wave frequencies are different. So the scope can only hold one nice and still in the screen, and if it's displaying another wave on the screen at the same time, then it kind of just runs it and it looks a bit of a mess. But the actual waves themselves, you can toggle between focus on probe 1 or probe 2, and the waves themselves actually look very nice in this case.
That few seconds of switch can cause heat if it's not happy. Bloop. Turn number 1 off. Yeah, that's looking very nice. Output switch, amplifier turned on. Boom, repaired. 1 FET. And I think that 1 FET going down must have just been from condensation, because for one single FET to go down like that, it would have to be an issue with the FET itself or something shorting that 1 FET alone. If it was an issue with, for example, customer wired a too low ohm speaker to the amplifier, then it would take out more than one at a time because they're all struggling to power that low impedance. Or if you'd short out the speaker connections, all of the FETs would be driving that. Most other issues that would cause the output section to die would be related to having more than 1 FET dying. So yeah, I think that was just condensation that killed that one, and one FET replacement is all we needed. Let's just check for heat again one last time. We got 9 volts worth of input, which is not very much, and the rail voltage is quite low. So what I'm going to do now is I'm going to plug the slightly bigger power supply in, which is still quite a low current supply, get the rail voltage to boost up higher, because I've actually had one of these amplifiers before where on 9 volts it was perfectly happy like this, and then as soon as you put 12 volts into it, they all got hot. So let's do 12 volts just to make sure. Cool, right, 12 volt input now, see what happens. Okay, much bigger wave here, and let's just turn that off, make sure there's no heat. Ah no, it's stone cold again, like legitimately freezing cold. Okay, leave it on for a couple of minutes then, and make sure it's still cold. Okay, it's been on for a few minutes now. Absolute freezing stone cold, fantastic stuff. Power supply as well. Well, there we go then, condensation, that's the only explanation I can give for that one. Nice, cheap, easy repair for this guy then. One amplifier, no issues. Well, we're going to bench test these obviously, but...
Yo, a few people in the live chat. Obviously in the UK over here it's 11 PM. I would like to know where everyone is watching from and where the majority of watchers are from. Because then what I can do is I can then do these live streams at a time when people aren't working. So a few people are saying that they're working at the minute, they can't exactly watch the stream right now. So I want to try and gauge a good time of day that marries up with the most people who are watching the stream, and most people that want to watch the stream and get the information when they're, you know, maybe come home from work, or they're not actually busy at that point in time, because it helps out with the live stream to do the live Q&A. So yeah, let me know. And I don't mind doing these live streams at like 2-3 AM in the UK, because I'm usually in the workshop till 2-3 AM anyway. I'm a bit of a night owl in that respect, so that's not a problem. But maybe if I'm doing it at like maybe 12 midnight, then the guys in the UK can still watch it, and other places around the world. But I imagine most of my viewership is from the States. So yeah, if that would be better to do it later, let me know, and I shall do that for the next one.
No obvious issues on the bench, and this one with a single FET dead. Cool, he'll be very happy, I'm sure. So we're going to bench the 1.4 first, and this is the one that didn't seem to have any issues that I could see. So got the foot pedal again hooked up to the big supplies now. Let's crack her on. So we've got the power supply caps charged now. Cool, okay, so now let's bench it. So we're going to take our screwdriver, we're going to hit a sine wave, which we should see on the screen. Number 1 needs to be on. Okay, so let's hit a wave. There we go, output. So let's go to the clip point. Okay, there we go, saw some clipping there, so let's back off a little bit. Let's find that point again. There we go, that's a bit of soft clip. So let's pause the scope on that soft clip. And let's also just check what the multimeter was saying the voltage drop was. 11.99. Yeah, 11.99 on the voltage drop. So, okay, cool. Let's work out what power that did. So we have 37.34 volts, and we have 1 ohm. So at 12 volt it did 1,394, so about 1,400 watts. And let's now sort that out for 14 volt. Okay, so we've got 2,041 watts. So this amp claims to do 2,500 watts, but I think that claim is at quite a high THD percent. That's around about the 1.2% THD. It might actually be a bit less. I don't have a wave analyzer to work out the correct exact THD percentage, but with a tiny soft clip like it shows on the screen here, I've been told that that equates to around about 0.5 to 1% THD, depending on how much of a small flat top and bottom you've got there. So very usable power, very safe power for the amplifier. It will do that all day long, no problem. So yeah, cool. 2,041 watts at 14.4 volts. Good stuff. Now let's see what the V3 does, and it's probably going to be a little bit less, but not drastically less, I doubt. Okay, now for the V3. So we'll probably get a spike when this tries to turn on, as it seems to suck a sharp, sudden demand of current. So we'll turn the power supplies on first, and we'll hit the remote. And this will probably go fast again. Ah, no, okay. Ah, that'll be because the V4 has pull-down resistors, so it was pulling the rail voltage down, when the V3 maintained the rail voltage and didn't need any current to switch on again. Fair enough. Okay, so now let's take our screwdriver again and let's find our clip point. Okay, clipping there we saw, so let's back off a bit. Let's try and get the wave looking as close to the other one as we can. I'm barely touching the gain knob here. It's so sensitive up at this level. Okay, that looks about the same. Yeah, that looks about the same. So let's see what the voltage drop was on this. It's gonna be 11.9 again, isn't it? Always is. Yeah. Oh, exactly 12. That's about the same. I'm just going to roll with 12 volts. Okay, cool. So let's power that off and see what this one did. So we have 35 volts instead of 37 this time. 0.56 at 1 ohm. That equates to 1,264 watts. And let's correct that then for 14 volts.
So with the bench test, the reason that we play just a pulse of this wave is because we are running the amplifier on a static load and to full power, and usually at this point the amplifiers have just been repaired, so this is like the first real test to see whether the repair was solid and the amplifiers will do their rated power. So we're checking that the rail voltages are both present and that the rail voltages hold high. We're checking that the drive wave can produce a decent looking sine wave on the screen there, and with the bench test, the reason that I just do a pulse is because obviously this draws quite a lot of power from my power supply setup, and if I was to hold the tone on continuously, especially with higher power amplifiers that I'm more used to doing this with, we might see considerable voltage drop across the power supplies, which would then cause the wave on the scope to clip. So what would happen is you'd start the tone and the wave would look clean, so then you'd be like, all right, well that's my clip point, that's the point where I want to bench it. But then after a couple of seconds the wave would start to clip because the supplies then are struggling and the voltage is starting to drop, because they can do a kind of immediate burst of power, but then they will level off to a kind of continuous current supply. So that's the reason why when we do the bench test we do just a pulse to allow for as much current as possible to enter the amplifier to work out its maximum power here. On a battery or a car system, you'd be able to hold it on for longer, or until I get my super caps and the other stuff in the workshop hooked up for the power supply. However, this isn't the only test I do. Once this amplifier does a bench test to rated power or to clipping point, and I'm happy with how it's performing, we do an endurance test where we leave the amplifier running for 45 minutes, playing continuous sweeps on a reactive and a static load. So, say for example a 1 ohm amplifier, we wouldn't leave it on a 1 ohm static load for 45 minutes because it will probably overheat the hell out. So what we do is we leave it on a 2 ohm static load, but also hook up a 4 ohm reactive load to give it some kind of reactive load to drive some back EMF, etc., from a Woodford coil in a motor, and that runs for 45 minutes. Amplifiers get pretty hot during that, but if it passes that, then we are safe to say that that is a successful repair, because that is quite a stressful scenario for the amplifier continuously over a 45-minute period.
Okay, wow, only 1820.88. That's quite a difference there. Yeah, wow. Might want to just do that again, make sure that's correct. Yeah, 35.5 watts, the same. So wow, yeah, nowhere near as much power. 200 watt difference. So because I didn't actually have to
I'm just going to pause that there for 1 sec because I kind of cut the video off a little bit short there. So the V4 of the Bassface DB 1.3 did 2050 watts RMS. The V3, which the only differences are it has half the number of rail capacitors, it's a slightly thinner board, and it's cheaper wire used between the output section and the terminals. That's really the only difference. The circuit is exactly the same, but just those small differences, thicker board, thicker traces, twice the number of rail capacitors, we saw an additional 200 watts RMS just from these small changes. And it gave me an idea to do a video where we take a relatively cheap amplifier like this, where the board is maybe a bit thin and they've cheaped out on some parts, and we try and see how much power we can get this amplifier to do by upgrading it a little bit. You can't really do too many upgrades to the amplifier, but I'm interested to see how much more power it can do by adding more rail capacitors, thickening the crap out the traces, adding really thick wire instead of these jumper bars. You can even sometimes add additional FETs to the output section and the power supply section. That doesn't make it do any more power straight away, but it will allow you to wire to a lower impedance, provided the drive circuit can handle it and the power supply section can handle it. And then we can even go deeper. We can take the transformers off and give them a few more winds to get the rail voltage up higher. That could be an interesting thing to do, and I'll choose an amplifier to do it with that I don't care about, because we'll probably end up blowing it up because I'll probably end up doing more and more and more windings until we reach the limit. So that could be a fun video.
Much in this video. I wanted to go through the board with you and show you what bits you should look out for and what bits usually need replacing if you have blown FETs in either of these sections. So we'll start with the power supply. Now the power supply, usually with these boards and amplifiers, it comes with some weird thing like a P65N60. This won't focus, but yeah, some 65N60, this, that, the other FET. If power supply FETs are burnt and dead, replace every single one of them. Careful with these boards because you can take the vias out quite easily and the pads, so make sure that you have a decent amount of heat, and the FET is very loose and wobbly. It just literally falls out once it's got enough heat on all the solder to come out. And you should replace these with IRF P3205, or they IRF 3205. 3205s anyway, very, very common power supply FET. When you're replacing with 3205s, you will see these are the gate resistors. Can I get in on those? Yes, these are the gate resistors, and they are a little resistor that goes in between the driver and the gate of the power supply FET. If you're using 3205s, these should be a 47 ohm resistor, which these ones are, 470 or 47R on the SMD resistor, and that will drive the 3205s nicely. If you have dead power supply FETs, then when you take the FETs out and you make sure you haven't got any solder bridges from your desoldering, you should fire the amplifier up on a small supply and make sure you have a good drive wave on all of the pads for the gates, and the drive wave will look like a square wave. It may change shape or get bigger as the amplifier comes on, and then it will probably turn off once it realizes there's no output FETs. And if the drive wave doesn't look good, then you have some drivers to replace. The drivers on this amplifier are very, very small, and they do die very easily. I have to remind myself which ones they are here because I've worked on a lot of similar amplifiers. Okay, these four little transistors here. Now these ones on this board, they have used the coding on the transistor is L6 and M6, and you need to put these back in the right places. I can't remember the exact product code of these, but if you type into Google M6 SMD transistor, then you get a nice website that gives you the correct model number for the transistors, which you can order from RS Components or DigiKey, Mouser, etc. Now, you could replace these with the L6 and M6. I have used, from memory, I think it's 2T and 2X. Also 1D and 2D that have worked perfectly fine as well, but obviously if you've got the option, then use L6 and M6, as that's what they have used on the originals. These are the driver transistors. You should probably replace all of them because they are cheap as hell anyway. And you've got four here, and these four drive this side of power supply FETs, and then you've got another four which are in here just above the IC. You've got another four there which they drive this side of power supply FETs. So if you have power supply FETs down in a bad way, more than likely you need to check these four and these four here driver transistors, and possibly if you're unsure or if you don't have a scope, absolutely replace them anyway. They're very cheap, so it's worth doing. It solves any potential issues that you may have missed. If you're replacing the driver transistors, it's always a good idea, seeing you've got the power supply hooked up anyway, with all of these transistors off the board, is to measure the wave coming out of pins 9 and 10 of this IC, and this IC is responsible for generation of the PWM switch wave for the power supply section and some of the protection circuit. This is usually a 494 or a 7500. As you can see in this case, it is a 494. And pins 9 and 10 are these two on the end here, 9 and 10. So if you fire the board up, you should get a little pulse of a square wave on 9 and 10. It'll disappear very quickly because it will recognize that there's no driver transistors in the board, but you can see whether the chip is working correctly just from the little pulse of a square wave it gives out, and then fit your new driver transistors, and then you should be safe then to fit the new MOSFETs on the output.
You know, I completely am blind because I didn't see that they actually had the part number written right next to the part that I was reading. Yeah, well spotted.
For the power supply without any further issues. If your power supply FETs have gone down in a bad way, then you need to check all of the gate resistors, these 47 ohm ones. If you're not changing them with 3205s for 47 ohms, check all of them. Go through with a multimeter and check every single one of them. Needs to be around about 47 ohms. It can be plus or minus a little bit of tolerance, but yeah, it needs to be around 47 ohms to be working correctly. And another resistor which you need to check is the pull-down resistor, which on each side of power supply you'll have one that is a 1000 ohm resistor, and that needs to measure 1000 ohms, believe it or not. And sometimes these either go completely open or they go short, and it will cause damage to the drive circuit if it's short, and if it's open then there'll be drive wave issues which will heat up the FETs. So always check the pull-down resistor, the 1000 ohm resistor, and check all of your gate resistors as well. And there is a 1000 ohm resistor there. I think there's one on each side. There's one there and there's one on the other side. No, sorry, there's two each side. 1, 2, 3, 4, because we've got 4 banks of FETs here. Yeah, so there's 4 pull-down resistors that you need to check, and they should all be 1000 ohm.
Just a quick one on the pull-down resistors. So every bank of power supply FETs will have one pull-down resistor that takes care of that bank. The purpose of the pull-down resistor is on the gate. So the gate of these MOSFETs is very sensitive. If there's 12 volts sitting on the middle pin of the MOSFET ready to go, then you only need a very, very small amount of current or voltage on the gate that can turn the FET fully on. And if you turn one FET fully on its own with the 12 volts from the battery behind it, then it's going to die. So the reason you have a pull-down resistor is firstly to make sure that when the amplifier is off, no kind of residual current builds up on the gates from static charge or from electrons in the air, which can happen. And the pull-down resistor also helps the drivers pull the drive wave back down to ground after it's done the upward cycle to turn the FET on, and then the pull-down resistor just helps it pull down to ground. But it's predominantly there mainly to pull down any residual current or static or anything when the amplifier is off, to prevent the amplifier from blowing itself up when you're not even using it.
If you've got good drive wave and you've got all new FETs and you can't think why else the power supply FETs are heating up if they are getting warm on a small supply, then wiggle around and check the transformers. Sometimes these vibrate against each other when it's amped mounted to a box, and the leads will short against each other. Not that common, but it does happen, and it can be an absolute headache when you fit an all new power supply section, everything you've changed, and they're still bloody heating up and not working right. More than likely you've got an issue with one of the transformers. So with it powered up, just pulse power it so that they don't get too hot if they are getting warm, and wiggle this around, see if it changes the shape of the wave as you wiggle it, or if they stop getting hot. If you've got one of these transistor tester, you can actually flip the board over and measure the inductance of the transformer windings, and then you can then easily spot a short because it won't show any inductance, it will just show a very low ohm reading. Output section then, obviously, other than changing these output FETs, similar to the power supply, we have driver transistors, and these are located here and here. And the driver transistors for this board are 2T and 2X. and they're actually nicely labelled on this board, but they won't necessarily be labelled on all boards. You have a 2X, 2X and a 2T, and these are the 3 driver transistors for this side of output FETs. And if the outputs go down in a bad way by the fact that there's more than one that's dead, either a short circuit on the speaker wires or some other issue that pull a lot of them down, then often these will be dead or they will be leaking. And so it's always good practice to change these anyway. 2X, 2T, very cheap. And the same goes for the other side. It's these 3 here, 2X, 2X and 2T. So if you don't have a scope and you can't see the waves, if you want to do a repair that should pretty much work every time on this amplifier, change all the output FETs for the same batch, check all the gate resistors the same as in the power supply section. These I reckon are about 10 ohm, yeah, 100, which is 10 ohms and 0 for multiplier, so that is 10 ohms. Check they are all 10 ohms. If they're not, replace them. You've also got a pull down resistor on the output section, which is a 103. That is a 10,000 ohm pull down resistor, to make sure that reads 10,000 as well. If you're unsure, replace it. These Zener diodes generally don't fail, but just make sure that they aren't a short circuit. If they die, they'll generally be a short circuit, so if they're not short circuit, then they'll probably be fine. And then just replace these 3 and these 3 with a new 2X and 2T, and you should be good to go. Same on the power supply section, just replace all the drivers, gate resistors, power supply FETs, and this pretty much will work every time. It's very unusual for this driver board to fail because it is buffered by a fair number of driver transistors, and the protection, once these start dying, is very quick. It cuts out before this really gets hit by anything, so you probably will never have to start removing this board. Very unlikely to have issues with the driver board in these amplifiers. So only if you have done everything I have previously mentioned and you still can't get the thing working, doesn't have good drive on the outputs, then yeah, maybe there might be an issue with this. But I haven't come across one yet with an issue here, and I've repaired a lot of these. If the head unit has spazzed out and thrown 12 volts or more down the RCAs, and that's blowing the amplifier, then you may need to replace these OP amps. Now these are literally all the same, and they just deal with parts of the crossover and all your adjustment knobs and sending the wave in from here to the driver board. And these are TL047Cs, and they're all the same. So just get a TL047C and drop it in, and you should be good to go. Again, just like the power supply section, if the output section you've replaced everything and it still seems to be heating up and you can't figure out why, there could be a short circuit on the inductor. So just make sure that it's not loose, and make sure that giving it a wiggle doesn't change the waves at all. Yeah, just make sure that, measure the inductance if you've got an inductor tester, whatever. But yeah, sometimes it fails, but not that common on these amplifiers, but it's always worth looking out for. Oh, also sometimes I've seen amplifiers with these capacitors here, they blow to bits. And they're not easy to find, but you can find them online. Just Google the code on the top and you'll find the correct ones eventually. Yeah, literally just replace them and it's fine.
Emeritus in the chat says, do you ever see the IRF Z44 FETs in the power supply anymore? Yes, I have, not too long ago. What was it I opened that had Z44s in? I've seen them in really cheap, like small monos or small class ABs, like, you know, your Walmart style, your Halford style amplifiers is the most common thing that I've seen them in. But the Z44N or the Z44s are actually really good FETs. They're not the most powerful, so you maybe need a few more of them to do the same current draw that maybe the 3205s could handle. But they are very flexible, and they work the easiest with each other. So out of all the FETs that I've seen, if you're gonna use different batches together, the Z44s are the ones to do it with. They don't care as much about the specifications of each other in a parallel bank. They're very flexible, and they can be driven by a variety of different drive circuits, loads of different frequencies. They don't need much to turn the gates on either. They're actually a very good FET. You suffer with the current handling and the power dissipation from them compared to a 3205, for example. But if they're quite cheap, so you can just add a few more of them if you've got space on the heatsink, and you should have a pretty reliable power supply circuit.
Very important to take note on these amplifiers, these V3s and other similar boards like this. If you don't see any big resistors around the output section, like around here,
someone mentioned this earlier,
then it probably doesn't have main rail voltage pull-down resistors, which means that when you turn the amplifier off, even if you leave it for a week, there will still be very high voltage sitting on these FETs and on the legs and in the caps. And so you come to work on the amplifier, touch your soldering iron on the output section, big spark, and maybe you kill some drivers. Yeah, so if you're working on this amplifier and you need to do some soldering on the output section after having it powered up, then you need to pull the rail voltage down to ground before you work on it. It needs to have nothing in the capacitors. So yeah, you can just flip the amplifier over, just use a 47 ohm or greater or lower if it's a big powerful resistor to short out the capacitor legs on the other side of the board to get rid of the rail voltage.
Okay, wicked. There we go. That ended quite abruptly. So that is quite an interesting way of doing the live stream repair video. So obviously the reason for that, I would quite like to do the repairs live, but until I sort out the camera setup, this seems to be quite a nice way to do it. And you don't have the ridiculous length of a live stream that you would have otherwise. I mean, some of these repairs that I'll do would end up being like 2 or 3 hours long, especially on a bigger amplifier, because you've got the whole disassembly and you've got all the soldering and everything that takes place. So perhaps this might be a good way to go forward for a lot of these repairs, and maybe I'll do legitimate live streams from the workshop if there's a small amplifier or something that I know what the issue is and I know it's not going to take too long, and that could be quite nice. Yeah, just in response to electronic artists, Z48s. I've not seen the Z48s in amplifiers yet. I will look up the specs of those and see what the jam is. But yeah, I've not come across an amplifier with the Z48s in yet. Let's have a quick look up the chat now and see what there's any questions I've missed or anything going on down here. So the power supply that I use for bench testing. It's a pair of Dell server power supplies. They're rated at 2,100 watts each, and that equates to 175 amps per power supply, and that is at 12 volts. So I use two of them, so I have 350 amps at my disposal. These Dell server power supplies are quite underrated. You compare it to like a car amplifier, the decent ones are all generally underrated and they'll do more power than they say. So you can actually draw quite a bit more power from these than the standard 350 amps with the pair. I've actually managed to bench up to around about an output wattage of getting on for 5,000 watts on these, which is pretty impressive. You do get a bit of voltage drop, so they're 12 volt power supplies. When I drop a huge load on them, I get about a voltage drop to 11.8. I would like to have them bumped up to around 14 volts, and you can increase the voltage on these Dell server power supplies to 14 volts by using the voltage sense return pin, and you apply some voltage like 5 volts through a potentiometer to the voltage sense return pin, and it tricks the supply into thinking that the voltage has dropped and it boosts it up to compensate, but it boosts it up past 12 volts. The only problem with that I find is that the boosted 14 volts is almost fake. It doesn't actually do any power. So as soon as you draw current from the supplies, it drops instantly back down to 12, even though you've got it boosted to 14. And that's only on the Dells. I bought some HP supplies, which are very similar to these Dells, that you can boost to 14 and they stay there. They can actually do the power at 14. I've just yet to hook them up. They don't come with fans, so I need to build myself a case with some fans to allow them to actually do the power without overheating, because these supplies are very small and they do a lot of power. And they're very reliant on airflow to not overheat when it's doing a crazy amount of power like that. Look forward to a video on Orion XTR or HCCA. Now those amplifiers, the HCCA series amplifiers, can be an absolute nightmare to repair, and the reason for that is they're actually a fantastic amplifier, really good amplifier design on the Orion HCCA line, so the 2400 and the 5000. The only issue with them on a repair basis is that the amplifiers are controlled by a PIC, so it's a programmable IC, programmable integrated circuit, and this is a bit like how to put it into concept, like a bias chip, or it's like a, it's a chip that is programmed with a specific set of tasks to control the amplifier. And in the Orion amplifiers, this PIC controls everything in the amplifier: the protection circuit, the power supply switch, how the output section works. Over time, these PICs are run quite hard and they tend to die. And the problem is, once the PIC dies, you got to go to Orion and ask for a new one. And at this day and age, I don't think I have any left. So if your PIC is damaged in one of those Orion amplifiers, then you're pretty much screwed, because you can't get replacement PIC. You can get the chip, but you don't have the firmware, the program to flash onto it, to program it with, that Orion has obviously designed. So yeah, the only way to make the amplifier work again is to bypass the PIC circuit completely and build yourself a new circuit that controls the amplifier based on more conventional methods, like how most of these amplifiers work. You bang a 494 in there with with some buffer transistors for the power supply, get the power supply working, bypass most of the protection circuitry. It can be done. I've seen it done. It's just a bit of a headache. Yeah, a bit like ROM. Yeah, a bit like ROM. Let's have a look. What else we've got in the chat up here? We had a question about why do head units output like 2 volts or 4 volts from the RCAs, but amplifiers state that they only need like 200 millivolts. So on the amplifier, if you look at the specifications of the amplifier, it will probably have a specification which says minimum input voltage, which will be something like 200 millivolts. Now that is with the gain on maximum. So that's the amplifier saying, I need a minimum of 200 millivolts in order to do my maximum rated power to clipping point, essentially at a specific voltage. Any less than that, and the amplifier won't clip or won't do its rated power even with the gain on full. If you put more than 200 millivolts into the amplifier's RCA inputs, let's say you put 2 volts, then the gain, you use it to turn the gain down to make the amplifier less sensitive to input voltage. So an amplifier that does 2000 watts RMS at 1 ohm with 200 millivolts worth of input voltage on the RCAs and the gain on full will do 2000 watts RMS. If you put 4 volts into the RCAs, for example, and you turn the gain to 0, it'll do the same 2000 watts RMS at 1 ohm. With 4 volts worth of input in the RCAs, if you then start to turn the gain up, the amplifier is already doing its maximum power. So adding any more gain will just put the amplifier into clip, because the sine wave that the amplifier is trying to produce will go up and above the rail voltage, which is why the clipping waves turn into a square, because it's trying to go up and above beyond where the rail voltages are sitting. Rail voltages are sitting maybe at like plus and minus 80 volts. If you try and drive the sine wave to plus and minus 100 volts, it tries to go to there, but it gets capped off at 80 and the same on the way down, which is why the clipping looks like a square wave. Common issues for one MOSFET to blow, pretty much condensation or just a dodgy FET, or a really fast protection circuit. If the amplifier had a fault where the drive was a fault, or the customer applied a too low speaker impedance, like a 0.25 ohm, and the amplifier couldn't handle it, most of the time you'll lose more than one FET. If one FET just dies and the others are perfectly fine, it's got to be an issue with that one FET. Bit of metal on the board from trimming wires that shorted that one FET out, or condensation that caused a leak current onto the gate, which turned that one FET on, and yeah, caused that one to blow, but the others were fine. Yeah, so the V3 Bassface has no pull-down resistors on the output section. So someone said about this, Tony Baker said that the boards are bad for having full rail voltage sitting on the rails at all times, so it's best to drain the rails before poking it around. Learnt the hard way. Definitely, I have also learnt the hard way on that one. It's no fun when you have 80 volts on the output rail and you touch the soldering line to the board. That is not fun at all. That's pretty, you get a bit of a wake-up call there. From an amplifier's operation sense, it actually is better to not have pull-down resistors, because it means every time you turn the amplifier on, the power supply hasn't got to charge them up again. And it means that with pull-down resistors, there's always a very small amount of load on the power supply. It's always powering this pull-down resistor that's trying to pull the caps down. So if you don't have the pull-down resistor, then the amplifier is just literally sitting in a very idle state with doing absolutely nothing, which is a better state for it to be in. The only reason that the pull-down resistors are there is so the amplifier can be worked on safely. But who cares about that? If the amplifier doesn't blow, then you don't need them. Yeah, I think I will do that video on upgrading the amplifier. So taking a cheap amp and seeing how much power we can squeeze out of it by making little changes to it. That would be a really fun video to do. I shall have to select an amplifier that doesn't owe me too much to do that with, and it's quite a basic board layout. I think that would be pretty good. Okay, let's have a quick look on here. So we've got 33 still watching. Okay, cool. We're going to lock off the stream on this one. What I'll do is I will continue this method for the foreseeable future for the repair videos. I will leave the streams up, obviously, and when I've finished doing a repair video and I've edited it, what I'll do is, rather than just uploading it, I'll do a live stream like this, and then anyone that wants to ask any questions about the repair, I can answer it then and there. And then until I get some better recording equipment, cameras, and the cost of RAM and graphics cards comes down from where it is in the clouds at the moment, I can then start doing live videos in the workshop whilst I'm repairing stuff, which would be much more fun. So thank you very much for watching, guys, and until next time, I hope you have a good evening and rest of the day.